Greetings. In the previous video, we learned from the mass conservation and the first law of thermodynamics, and now we move to the second law of thermodynamics and the availability equation to see what do they have to teach us. How would the second law of thermodynamics look like for this compressor? Now, if we look at the second law of thermodynamics, this term would vanish since the problem is steady and there is no change of whatever there is inside the control volume. So the problem ends up with these four terms. The entropy that enters with entering mass, the entropy that leaves with the leaving mass, with the exit mass, heat transfer, which is 0 for an adiabatic compressor, but it has some value for the isothermal compressor, and S dot Gen, which we shall discuss it now. So let's write down this equation and see for a third compressor that we shall introduce now how that would look like. You see, the equation would reduce to 0 equals m dot ISI minus m dot ESE plus Q dot over TB and plus S dot J. This is how this equation would look like. Now, a third process, which is of interest to us, is an isentropic process, which is an adiabatic and reversible process. So we want to talk about adiabatic, reversible process. You see, this process is a very key process. The reversible process is the one that is a reference process. It's a process that we can do all sorts of calculations for it. And it's the reference, which is the boundary condition between the possible process and an impossible process. In the reversible process, S dot Gen is 0 and Q dot is 0. And therefore, it ends up to be 0 equals m dot ISI minus m dot ESE. And that means SI would equal SE. Let's draw this on a TS diagram. If we draw a TS diagram, this is a TS diagram, and constant pressure lines on this diagram would be these lines. This is 120 kilopascals, and this is 1000 kilopascals. Okay, now our initial point I is here, where the temperature is 293. Kelvins. And at least we know for the isothermal process that the final point is here. So E for the isothermal process would be here at the same temperature. Now, the adiabatic reversible process, where SI equals SE, would look like this one. This would be E, and let me call it E prime. And I usually call the reversible process and denote it with a prime. So this is E prime. The question for us is that is this E prime warmer than 300 degrees C or cooler than 300 degrees C? The question is that is this process that we have drawn, would it be to the right of this line or to the left of this line? That's the question, which somehow we could answer it because we know that if the process is reversible and adiabatic, then this is the leftmost entropy that we could attain. And a real process could only increase entropy, and therefore the process would be to the right. I mean, if we write down this equation for this process, the process that I have shown here, the red process, then this equation for a real equation, for a real process, zero equals m dot I Si minus m dot E Se plus q dot over Tb and plus S dot J. And for a real adiabatic process, this term vanishes. Of course, it is a real process plus adiabatic process. This term vanishes, and therefore Se m dot E Se would equal m dot I Si plus S dot J. And since S dot J is always positive by the second law, therefore this term would be added to a positive value, and therefore the final entropy would always be larger than the initial entropy. The question is not that if point E is to the right or to the left. The right question, the correct question, is that is point E on E prime or to the right of it, and which one is true. And the best way to know this is to calculate the temperature for E prime. It's a very simple task. T prime for the isentropic process equals Ti times Pe prime over Pi to the power gamma minus 1 equal over gamma, which is 293 times 1000 divided by 120 to the power 0.286, which is 1.4 minus 1 divided by 1.4. And the outcome for Te prime is 537.3 kelvins. You see, this value was 573, and this is 537. So it means that the temperature here is 537.3, and the temperature for our point is 573. So this would be point E, and its temperature is 573 Kelvin. This was the process that we drew with red. I I would repeat it with red here. This process was this one. Okay, this was the process for isothermal, and this IE prime is for adiabatic reversible process. In order to show the difference between a real process and an isentropic process, and show how far away a real process is from the isentropic process, usually they define an isentropic efficiency for the compression C. And the isentropic efficiency is usually defined as HE prime minus HI divided by HE minus HI. Why it is defined like this? You see, I did write the second law of thermodynamics for an isentropic process. I didn't write the first law for it. And what is the first law for it? The first law for it is very simple. I write the first law of thermodynamics for the isentropic process. And how do I do that? It is 0 equals m dot times Hi minus He prime, and the isentropic process has no heat transfer, and minus W dot prime, which is different to W dot. You see, this was the equation that I wrote for the real process. 0 was equal m dot Hi minus He minus W prime, and here the end point is E prime, and therefore the work is W prime. The mass flow equation is very the same, so the mass flow doesn't change, and I wouldn't write it. Now, the original equation for efficiency is the ideal work W dot prime divided by W dot, which equals m dot times He prime minus Hi divided by m dot times He minus Hi. And m dot cancels out. There is a Cp0 which also cancels out, and eta equals Te prime minus Ti if we just factor a Cp0 and write He prime minus Hi equals Cp0 times T prime minus Ti, and do the same for the denominator. That would be Te minus Ti, and that equals 537.3 minus 293.15 and divided by 573 minus 293.15, or I have sometimes ignored it. That doesn't make much difference, and the outcome is 0.872. That means efficiency of this compressor is 87.2%. 87.2%. That's the compression efficiency for this compressor. So the next step, are we able to calculate the generated entropy for this compressor? And the answer is yes, we are able to calculate the generated entropy since S dot gen, since S dot gen equals m dot times SE minus SI. You see, all I've done is to use this equation. All I've done is to use this equation and put SI to the other side. So SE minus SI, SE minus SI equals m dot, which is 0.01427 times delta S, which for perfect gas, we have a very good equation for it, which is Cp0. I would write the equation for it, SE minus SI, and these are not capital S, these are small s, equals Cp0 ln T over Ti minus R ln P over Pi. And this is 1.0045 ln 573.15 divided by 293.15 minus 0.287 ln 1000 over 120. And the outcome for SE minus SI equals 0.0000927 kilowatts per Kelvin. That's the value for the SGen. That's the value for SGen in this compressor. You see, this is our compressor. What we have done is we have calculated the difference between I and E, different entropies. You see, we have calculated this distance. This is the distance that we have calculated. This distance is SE minus SI. This is the distance we have calculated, and the equation tells us that this distance equals the generated entropy. It wouldn't make any difference if we had calculated SE minus SE prime. It would produce exactly the same result. But as it is, we have calculated it and we have found this value. We now know everything about the real process, the isentropic process, the efficiency, and also the generated entropy. The final step that we could take in this problem is to calculate the entropy generation for the isothermal process, which is this process. What happens here? All we should do is to write down the same equation for an isothermal process, and it would look exactly like this. The steady state, it would look like this. And since the work we have calculated is for reversible process, then all we could do is to cancel this one. We couldn't do anything else. If it wasn't a reversible process, we had no way to calculate work. So it is 0 equals m dot I si minus m dot e se plus q dot over t b. This is the value that we have. I would write it in Greek just to keep with the practice that we are doing this for isothermal process. This is for isothermal process. You see, this was our written is for isothermal process, and I would keep doing that for it. Now, are we able to calculate Si minus AE? Are we able to calculate the change of entropy between these 2 points? If we could do that, then we could multiply it by TB and calculate Q dot. Let's see, how does it look like? Si minus Se, which these two are capitals and results of these two, is equals Cp0 ln Ti over Te minus R ln Pi over Pe. And it is constant temperature process, so this term cancels out for isothermal process, and therefore we are only left with this one. Si minus Se would equal minus, and you have to multiply this by m dot just to calculate the total value. It is 0.01427 times minus 0.287 ln Pi over Pe, which is 120, divided by 1000. And the outcome would be 0.008683 kilowatts per Kelvin. And that is the difference between the entropy of these 2 points, which, as we expect, is larger than this entropy, the change that we had for our real adiabatic process. Heat transfer actually usually transfers more entropy than the entropy generated. You see, there's quite a difference between these 2 entropies. And the difference is this. You see, this term, this change of entropy, is due to irreversibilities inside this compressor. Okay. Now, this change of entropy, it is because some heat transfer has happened from this boundary, Q dot. And this is the entropy transferred by heat transfer. And this difference is the entropy generated by irreversibilities. You see, once you calculate this one, this is the entropy transferred by heat transfer. And once you calculate this one, entropy generated by irreversibilities. This one should always be positive. This one could be positive or negative. And you see, This term, if we write down this equation, you see, this is positive and this one is negative. So this should go to the other side and both be negative. So it is correct and makes sense. Now, one step that we could take very easily is to uh, calculate the heat transfer from this equation. For the isothermal process, Q dot over TB equals the change of entropy. So if we multiply this by 293, we could calculate the heat transfer. And let's do that. Q1, Q between I and E for isothermal process, which I am writing up for in green, is 293 times minus 0.008683, and the heat transfer would be minus 2.5455 kilowatts. This is the heat lost, and therefore its sign should be minus. There should be a minus sign because it is heat lost, and it exactly corresponds with this equation. The final step that we could take is to have a look at the availability equation and see if the balance checks. This equation, this equality checks. As it is steady state, this term vanishes. There's no change in availability inside the control volume. There's an availability entering with entering mass, availability leaving with leaving mass. Well, heat transfers some availability, depends on which one how you look at. There's an adiabatic compressor with no heat transfer, and there is an isothermal compressor with some heat transfer. Um, there is work, of course. There's no change in boundary, there is no change in volume, and also there could be irreversibilities, at least for our original compressor. There are irreversibilities. Let's calculate these, this equation for our two compressors. First, we do it for our first compressor, which is the our original compressor. I mean this one. This one. This original compressor of ours. I would first calculate everything for this one. And that is 0. So the equation is 0 equals m dot I AFI minus m dot E AFE plus 1 minus T0 over TB Q dot minus W dot, and I would just ignore that dV P dV CV divided by dt and minus T0 S dot Gen. And for the adiabatic compressor, this term vanishes, but this term vanishes, and there will three terms remain. One is the change in availability between inlet and exit streams, and work and the irreversibility. AFI, M dot I, AFI, minus m dot E AFE would equal m dot times HI minus HE minus T0 times SI minus SE. And that's how it should look like. Okay, therefore, let's insert values to it. This would equal m dot, which is 0.01427 times HI, which is CP0 1.0045 times TI, which is 293 minus TE, which is 573 minus T0. We have to define some value for the ambient temperature. Let's call it 15 degrees. We should make it 288 times Si minus Se, which is 0.065. Of course, we once calculated this value for all the total value. Now we are multiplying it with mass, so it should be for specific entropy. And the outcome would be AFI minus AFE m dot times AFI minus m dot times AFE would be minus 3.7465 kilowatts. Okay, this is the value for this term. Now for our real compressor, this term is 0 since it's adiabatic. We know the work. And we know T0 start gen. We can calculate it. Work was W dot was we calculated previously minus 4.014 kilowatts, and T0 S dot gen is T0 S dot gen would equal 288 times 0.000927, and the outcome is 0.26716. And let's replace everything in this equation. 0 should equal minus 3.7465 plus 4. This is 0. This is work. Work was negative. Multiplied by this negative would be positive 4.014 and minus 0.26716, and the outcome 0 equals minus 4.014 plus 4.014, and the equality checks. So that's how you could calculate the availability equation and check that all terms hold. When I was talking about isothermal process, I managed to calculate work from this equation minus integral VdP, and it ended up to be minus 2.5415. Later, I moved to the second law and managed to calculate heat transfer to be 2.5455. The two were calculated from different equations, not from the same equation, but the values are pretty close. And is it surprising, or is it natural? Should they be exactly the same? And the answer is yes. In the isothermal process, enthalpy is a function of temperature, and therefore, for a steady isothermal process, Q dot and W dot are equal. And therefore, it's no surprise that although we calculated that from this equation, we could have calculated W dot and then use this equation to calculate Q dot. Fair enough. But we did use a totally different equation, the second law of thermodynamics, and all the same, the result was very close, and Q dot was equal W dot. Another step that we need to take before we finalize this problem is to write down the availability equation for the isothermal process. So what I want to do now is to write the availability equation for the isothermal process and see how this would balance. And the equation would look like this. You see, if I write down the original form of the equation, it tells me that the change of availability within the control volume equals the change of availability between incoming and outgoing mass, the availability transfer with heat transfer, availability transfer with work, and change of volume, and also irreversibilities. And what we have in the isothermal process is that we have assumed that to be reversible, so this term vanishes. There is no change in volume, so this term would also vanish, and the problem is steady, so this term would vanish. And we would be left with a simpler form of this equation, which is 0 equals m dot I AFI minus m dot E AFE plus 1 minus T0 over TB times Q dot and minus W dot. We almost have everything to calculate in this equation, and that would be m dot. We would factor m dot from both sides. That would be m dot this would be m dot times AFI minus AFE is HI minus HE minus T0 times SI minus SE. And the rest would remain as they were. T0 over TB times Q dot and minus W dot. I would calculate these terms individually to see how they would contribute to this equation. 0 equals 0.01427 times, of course, for an isothermal process, delta H is 0 because H is a function of temperature, and since temperature is constant, therefore enthalpy is constant. So this would be 0 minus 288 times 0.6085, which is the change of entropy for the isothermal process. This is the change of specific entropy, and plus uh, 1 minus T0, which is 288 divided by 293 times Q dot, which is minus 2.5455, and minus W dot, which is minus 2.5415. And I shall close this parenthesis here. Okay, now I've calculated individual terms, which is 0 equals minus 2.5, which is the change of flow availability, minus 0.04344, which is the availability transfer rate. Heat, minus 2.5415, which is the availability transfer rate work. And this should be a positive sign here. And the sign here should also be positive, since work is done, it's negative, and is multiplied by this minus, and it would be also positive, and the outcome is 0 equals minus 2.54344 and plus 2.5415, which is almost equal, and the equality checks. It's worthy to note that how much the availability equation is different from the first law of thermodynamics. Look, let's see what was the enthalpy loss. Enthalpy loss was m dot times delta H, and if you calculate that, the value would be 4 minus 4.0136 kilowatts. In fact, it's not a loss, it's enthalpy gain, because it's you should call it enthalpy gain, because work is done and it has gained enthalpy. But how much flow availability has it gained? Flow availability gain, flow availability gain is minus 2.5455. So flow availability gain is less than enthalpy gain. Now heat transfer is minus 2.5455 kilowatts. Availability transfer with heat transfer is far less, is minus 0.04344. You see, since the um, temperature is not that different, it's isothermal process, and the temperature is very close to ambient, then although heat is transferred, but that heat doesn't carry much availability because it's not hot. It's almost at the same temperature as the environment. And finally, work. So these two come together. And finally, work, which is minus 2.5415, and availability transfer with work is exactly the same because work is of the same nature as availability, and they are the same thing, 2.5415. And this is how the first law, these first terms decide how the first law, and the second terms how decide how the first and second law together, and the availability equation hold. So I hope you learned from this lesson, from this practice, and cheers.